So guys, before the recess, we had a discussion on generation of AM signal. We were using square law modulator. So square law modulator is a kind of a block consists of couple of things. The important thing is your nonlinear device, which we saw a diode in our circuit, and after that we have a band pass filter. Now we are going to study that how we can demodulate the received AM signal at the receiver end. So we need to get back message from the AM signal as well. So for that we have a lot of techniques to do. The first one is just like we had square law modulator, we have square law demodulator. The second technique is envelope detector, which is very famous. When I say envelope detector is very famous, then I mean to say that GATE asks a lot of question on envelope detector. So we'll go into full detail there. The third one is synchronous detector. Synchronous detector is also very you can say important topic. Synchronous detector means like you have to just match the carrier frequency at the receiver as well as the transmitter side. So with that we can start. So put the heading demodulation of AM signal. Demodulation of AM signal. So first technique, let's start with first technique, square law demodulator. Square law demodulator. Okay. So guys, the block diagram is pretty simple. We have received AM signal. It goes into non-linear system. And the output goes into a low pass filter. LTF is guys low pass filter, and output of this is your empty. So let's call it as this is your input signal V1T, output of non-linear system is V2T. V2T. So V1 is your AM signal. So let's write the equation of AM signal, which is what? AC cos 2 pi FCT plus AC KA MT cos 2 pi FCT. Now V2T is square law, same funda, nonlinear system, so it will be an equation of A V1T plus B V1 squared. Okay. Now we are going to do a lengthy calculation, guys, here. So what would be V2T for us? It will be A times AC cos 2 pi FCT plus A times KA MT AC cos 2 pi FCT plus B times V1 square T, means square of this term, the complete term, square of this term. So write AC square cos square 2 pi FCT plus AC square KA square M square T cos square 2 pi FCT plus 2 KAMT AC square cos square 2 pi FCT. Okay. Now if you look at this, right, it's a long expression, right? It's a very long expression. Now it will go into the low pass filter. So again you have to do the same thing, you have to find the frequencies, right? So if you have to find the frequency, you can clearly need to understand that what is the cutoff frequency of low pass filter. So guys, cutoff frequency of low pass filter is from minus 10 kilohertz to 10 kilohertz. That's it. And assume MT is band limited to 10 kilohertz. Another assumption which we had was FC is equal to 1 megahertz means 1000 kilohertz. And then we can get it rolling. Now if you look at here, so you know that this will give you carrier frequency 1000 kilohertz. So I am writing term by term. This will give us 990 to 1010 hertz. 1010 kilohertz, we know that. 990 to 1010, 1010 kilohertz. This will give you, you know that, this will give you what? This will give you AC square by 2 plus AC square, AC square by 2 plus AC square by 2 cos 4 pi FCT. So this will give you a frequency 0 kilohertz and 2000 kilohertz. Correct, guys? This will give you this. Look at the arrow. This will give you 20 kilohertz minus 20 to 20 kilohertz because of this m square t, and because of this cos square. Okay, so it will be 1 plus cos 4 pi FCT m square 2. So it will be from 980 to 1020 kilohertz. You'll get another term, this also. Okay, we are good. And we'll get this. This is the signal which we are looking for. It will give you what? It will be also be written as 1 plus cos 4 pi FCT. So it will give you minus 10 to 10 and 990 not 990, sorry, because it will be cos, well, it will be cos 4 pi, so it will be not 980, it will be 2000 minus, so it will be 1990 to 2010, and guys, similarly it will be cos 4 pi, so it will be 1980 to 2020. Please change it, guys. 2020. I know it looks so complicated, but it's not that if you pay attention. Guys, our aim is to get massive signal. You can clearly see we get massive signal here, not anywhere else, right? Now what is the problem? The low pass filter will pass, it will not pass this term, KMT, it will give you 990, it will not pass this term. This was our aim, right? The whole part is gone, okay? It will not pass this. It will give 0 kilohertz and 2000 kilohertz. So it will not pass this term, but you will get at least BAC square by 2. Okay, that's okay. And here you will get minus 2020 to this. You will pass this, but it will not pass this. It will not pass this, but it will pass this. Okay? So what is happening? It will only pass m of t and m square t. That's what I'm trying to say. Because m of t is what? Minus 10 to 10 and m square t is minus 20 to 20. It will not pass any extra term. And even it will not pass the whole m square t. It will pass a subset of that. So let me show you how does it look. So final V output T, you will find this. Final V output T is equal to B AC square, B AC square K square, B AC square K A M of T. So guys, this is this term, okay, plus B AC square K square by 2 M square T. Okay. So guys, this is to your signal. You please do step by step in detail, you will reach here only, don't worry. And this is your noise. So what will happen, this is kind of your empty signal, minus 10 to 10. And on the top of this, you have a, minus 20 to 20. This is M square F. And on the top of this, you have a low pass filter, which will try to pass this much. It's an ideal low pass filter. So what is happening? You are anyway getting this, but this extra thing will also come on the top of the signal. Yes or no? Okay, I will do that. That's a valid concern. Next time they change the window, I will ask them to intimate you. Sorry for the inconvenience. So if you look at this, guys, this looks very complicated, but if you go with the concept I have given you and what I am going to ask you now, please, since I have done a little, jumping the steps, given the reason that you need to go fast when you are in the paper. So what you can do, you take it as a practice exercise, simplify everything, write all the frequency and use low pass filter. Are you getting the right equation? This is the equation you are getting or not. That you can do, validate. If any question, we'll take in the next session. Chetkar is asking why M square will pass, it's out of 10 kilohertz. So Chetkar, to answer your question, it will not pass the complete M square T, it will only pass a subset of it, which I have highlighted like this, zigzag. Because ideal low pass filter will say, okay, I am running from minus 10 to 10. So this part of this M square F, it is still, inside this ideal low pass filter. So it will pass, right? Okay. So how the output will look like in terms of spectrum? So output spectrum will look like this. See, this is what you are supposed to get. You are supposed to get something like this. But are you going to get this? No. What will happen? It will have some noise because of that M square T. This is what you will get. That what did you do with this AC square by 2 term? Very good. See, it will be passed through the low pass filter, but any AM receiver will always have a capacitor to block any DC term coming through. So since we are having analog circuits in place, so it has capacitor, and you know what is the property of capacitor. Capacitor blocks the DC component, and that is the reason I didn't write AC square by 2. Got it? But I intentionally left that for anyone to pick it out. Okay, somebody is attentive enough or not. So I generally do that so that I can also see how many of you are attentive enough to figure it out. Sir, what did you do with that AC square by 2 term? And then I answer it. Very good. If nobody is noticing, I pass it off. Now guys, second technique, envelope detector. Envelope detector, ED. It is widely used technique. Widely used. So guys, you know that in AM signal, if you have a kind of, I showed you, right, that where we were like trying to find that equation, right, mu equal to V max minus V min upon V max plus V min. So there I showed you, right, how the envelope of the any AM signal will look like. So just write one point. In amplitude modulation in AM, the peak amplitude of the carrier the peak amplitude of the carrier, which is also called as envelope, is varied according to the masses signal. Is varied according to the masses signal. So we can say that. So the envelope of AM signal. So the envelope of AM signal represents the masses. Envelope detector is used to track the peak amplitude of the AM signal. So guys, envelope detector main job is to track the peak amplitude of the AM signal, and the moment you track it, you get the AM signal itself. Okay. Circuit for this. So we have AM signal as the input, source resistance with a diode, a parallel capacitor with a load resistance, and V output is actually VC, which is voltage across the capacitor. Okay. So you know that when the diode is forward biased, the capacitor will get charged, and when the diode is reverse biased, capacitor will get discharged through this load resistance. Can you see it? So when the capacitor is getting charged in one cycle, then in the another cycle it will get discharged, and the whole focus is on the discharging of the capacitor. One assumption though. So assumption is capacitor is initially uncharged. Capacitor is initially uncharged. Now we are going to draw a series of diagram, okay, so that we can demonstrate how does envelope detector work, right? Okay, so this is minus A and this is A. So this is your masses signal. In this, what we have done, we have added M of T plus 2A. So you will go where? So this 0 will go to 2A. So let's say this is 2A, this is A, and will go to till 3A, something like this, and this minus A will come to 0. No, minus A will come to plus 2M is A. So here. It will be something like this. Yes. And 0 will come to 2A. Just take this out. Okay? But your focus should be on this dark curve rather than looking at the dashed line. Okay? Now, why I have added a DC term? So that you have seen in A, you add AC cos 2 pi FCT, so then you take it common, it becomes 1 plus. So that 1 plus you thinking as 2 plus, 2A, right? Now you're going to multiply this with a carrier, which I'm drawing, guys, just below it. Little difficult to see, but you will have a quick idea. Let me draw it there, guys. It's too congested here. So let me draw here. I'm drawing a carrier here. So carrier is AC cos 2 pi fct. So that's why it is AC and minus AC. So it will go like C. So roughly I have drawn a carrier here. Now what will happen if I multiply, let's say 1 and let's say this is 2. So if I multiply 1 into 2, I'll get the AM signal. Yes? So it will be something like this. 2A minus 2A. Yeah, I'm doing rough diagram. So, and the carrier will look like this. Okay? Clear? So guys, this is your AM signal. And the part which you are seeing, this is your 2A plus empty part. And this is, guys, minus 2A minus M of T part. Now how the envelope detector will work? Envelope detector will take what? It will go and quickly charge till here. Okay? So let me show you that part easily. It will quickly charge and then it will not, not go like very, not discharge very quickly. It will not discharge like this. What it will do? It will go little discharge and again charge, little discharge, again charge, little discharge, again charge, little discharge, again charge. Similarly, you will see a zigzag signal like this. And the moment you take this out, it is 2A plus empty, and then it goes into the low pass filter. Capacitor will block this DC term. You just get M of T. Sorry, no need to pass through the low pass filter. You just block the DC term and you will get M of T. Now guys, you might be feeling that it has a lot of distortion. Right? I know. You might be feeling that it has a lot of distortion. But if you look at here at big, little big, so you feel like there's a distortion. I know that. You feel like there's a distortion. But guys, you forgot one thing. What is the frequency of carrier signal? Carrier signal frequency is 1 megahertz, which is like 10 to the power 6 hertz. Means, what is the meaning of 10 to the power 6 hertz? The meaning of 10 to the power 6 hertz is this, that you will see 10 to the power 6 cycles in 1 second. And that's too much. So your carrier will not look like this zoomed in version which I am showing on the screen. It will be so closely packed. Let me show you. It will be so closely packed that you will not have any much space to even go, I know it's very difficult to draw like that, but let me do my bit. Now here looks a lot of distortion. If I say, how does it look here? Come on, tell me. Guys, do you feel that distortion is less here? Yes or no? Just respond. Do you feel distortion is less here? Just imagine if it is too closely packed, there's not even this much space, how the capacitor will discharge and go down. Right? It will not go down like as you see here or as you see there. It will be like slowly it will go discharging like little this much up, and this much up. Right? And that's how envelope detector works. But if you take our AC circuit, which is having a frequency of only 50 Hz, like household circuits, right? In our home, you have frequency of 50 Hz. Frequency of 50 Hz is too bad, right? If you compare carrier signal. So it is something like this. Now if you try to find, then it looks too much distortion. And that's why in half-wave rectifier circuit, you calculate ripple factor. There will not be ripple in here, but there will be ripple in AC circuits at our home because their frequency is only 50 Hz, but here frequency of carrier is 10 to the power 6 or like a million Hz. A million Hz is like 10 lakhs Hz. 10 lakh Hz is like too much big number as compared to 50 Hz. And that's why the distortion of receiving the output signal is almost negligible. Are we clear on that? Now guys, there's one important topic related to envelope detector is this choosing the right discharging time constant. So you can put the heading in envelope detector. So guys, I told you that in the circuit I showed you just now that discharging time constant will be tau discharging will be equal to load resistance into capacitance. Now if the discharging time constant is not in balance, then what is the problem? Take case first. Case 1, when discharging time constant is short. Now if it is short, what will happen? Means it will quickly discharge, right? So what would be the problem? The problem would be, let me draw the diagram and show you guys. So we had our, AM signal, something like this. The carrier here. Okay. Now discharging time constant is short, what will happen? That it will quickly discharge, so it has to track this signal. Okay, let me use some color, other color. This is what I want, right? This is what I want, but what it will give me is something like this. It will discharge and it will discharge fast, and then this up, again fast, up. So it will give something like this. See? So what is the output you get? You are supposed to get that. You are supposed to get this. You wanted this, but what did you get? You got something like this. Something like this. Yes or no, guys? When discharging time constant is short. Okay? What if it is more? If discharging time constant is long. So again we'll take the same AM signal. So it is the carrier signal is this. Okay. Now if discharging time constant is more, it will very slowly discharge. So here it will not be a problem. See, you are supposed to get this. You are supposed to get this. So when it is like here, it is not a big problem. It will go slowly discharge. It will almost go there. Okay, take it. But now what is the problem? This is going very low. The massive signal is going, the AM signal is going low, very low, but it will slowly discharge, and after that it will slowly discharge, it will reach and then it will pick it. So what is happening here? You see this diagonal line. This diagonal line, can you see it? It is diagonally jumped because none of the this point is giving more value than this. It will slowly keep continuing discharge until it reaches here, and then you get another little more signal, more positive value. You charge a little bit more. So what you have missed? You have missed completely this part of the AM signal. You have missed this part, and that's why it is known as what, guys? You must have heard. This is known as what? Clipping. Diagonal clipping. Yes or no, guys? Come on, tell me. Why is it called diagonal clipping? Because it has diagonally clipped the AM signal, some part of the AM signal. Trust me, nobody will tell you in the way I have told you just now. It is called diagonal clipping because it is diagonally clipping one part of the AM signal, because discharging time constant is too big and it is too long. It is discharging very, very slowly. Okay? Okay, I can repeat that. See, in case 2, what happened? Discharging time constant is very high. Means the capacitor will discharge very slowly. Now what is happening, brother? If you charge this, it is fine. But when you go in this region, right? So capacitor gets discharging, then here it got charged a little bit. Now after that, when it is discharging, there is nothing, no wave, no cycle is able to charge it because it is discharging very slowly. If it would have been discharged little more faster, it would have come here and then again discharge, right? It would have come here and again charge. But what is happening? Discharging so slowly that every time capacitor voltage is more than the input voltage, right? Capacitor voltage is always more than the input voltage. So what is happening? It will keep continuing slowly discharging like this, and then you see another cycle is coming and it gets charged. So, but you are supposed to go like this, right? You are supposed to go like this. You are supposed to go like this. But how did you go? You went directly. It's like, suppose you have to go through like that path, but it went directly. But in AM signal, it will not work. You need that signal to track exactly how the waveform is going. So this is known as diagonal clipping. Why it is going directly? Because the capacitor is discharging very slowly. If it is discharging very fast, that's also a problem. If capacitor is discharging very slowly, that's also a problem. That is the reason we say that capacitor discharging value, which is RC, should be less than 1 by Fn, and it should be greater than 1 by Fc, and then we are happy. To avoid diagonal clipping, so this part is important to avoid diagonal clipping, that it should be less than 1 by Fn. Guys, time constant is tau, right? Tau is time constant. Time constant is like 1 by Fn, right? 1 by any frequency. So that's how the condition is there. So always keep in mind, very important, put in 2 star. Get an ask question. I will also solve. RS, this discharging time constant, I have just written in terms of a generic manner. You can also write RLC is less than 1 by Fm and it should be greater than 1 by Fc. If this condition is not fulfilled, you will have either of these problems. You will get distortion, or like that I showed, or you will see diagonal clipping. So if it is not more than 1 by Fc, you will see distortion. Means it is discharging very fast. If it is discharging very slowly, you will have diagonal clipping. So keep in mind. So guys, some important input-output pairs. Input, output. So what I am going to ask you, that when you get these signals into the input of envelope detector, what is the output? So first one, if you get any signal, let's say 10 cos 2 pi FCT to the envelope detector ED, what is the output you get? Output would be, guys, only 10. Envelope is 10, the constant line. Okay? If I just replace 10 with AC and then again write 10 cos 2 pi FCT going into the envelope detector, what will I get? I'll get output as only AC. Suppose I change this and AC with e की power minus t cos 2 pi FCT and give it to the envelope detector, what will I get as output? I'll get as e की power minus t. Fourth one, guys, if I give any signal which is something like this, a cos 2 pi FCT plus b sin 2 pi FCT. If I give this signal as input of the envelope detector, what would be the output? Now guys, you have to convert this into a single trigonometric term. For that, what you can do, you can multiply and divide by this term. It's a manipulation, guys. So you write cos 2 pi FCT plus b by root under a square plus b square sine 2 pi FCT. Okay? And actually you can write it as sine theta cos 2 pi FCT plus cos theta sine 2 pi FCT. Basic trigonometric identity you can make it, and then you can write it as root under a square plus b square sine of theta plus 2 pi FCT. And this is going to the envelope detector, and you know that if it is going to the envelope detector, you will get the amplitude, which is root under a square plus b square. Very interesting question. Although I am giving as point, but it can be a question also down the line. So in the similar fashion, if I ask you that input is AM signal, which is AC1 plus KAMT cos 2 pi FCT going into the envelope detector, what would be the output? You know, output would be just coefficient of, or you can say just the amplitude of this cos. So you get AC1 plus KMT. Now guys, here is a catch. Now what is the catch? In all of this there is a catch. If mu is less than 1 or even equal to 1, then do you get this only, AC 1 plus KMT. But the moment if mu is greater than 1, it is a case of over modulation, and then output of envelope detector is not equal to directly this. Actually it is equal to AC 1 plus KMT ka mod. GATE has asked a question on this. Already they have asked a question. Okay, please note it down. Very, very important note I have given you. It takes mod of that signal. Okay? Suppose you have a message signal going from -5 to 5. Okay, so it is something like this. So this is 5 and this is -5. In this, you add +3. What will happen if you add +3 volts? So this 5 will become 8 and 0 will become 5. So I would say this is 5, start, goes up and will come little down. So this is 8 Minus 5 plus 3 will become, you know what? Minus 2. Now if you modulate this signal with the carrier, what you will get? So you'll get something enveloped like this. So this is 5. This is minus 5. Correct? In this you will have a carrier embedded like this. The moment it crosses 0, magic happens. This is my AM signal. Okay, so what is this? This is 8 and what is V minimum? Minus 2. Okay. So guys, here V max is equal to 8 and what is V min? Equal to minus 2 volts. Yes or no guys? Now if you apply this output goes into the envelope detector, what are you expecting to get? You are expecting to get, follow my marker, expect to get this signal because this is your empty. What you will get actually? You will get this. This and then it goes up. Because the envelope detector just detects the peak of the signal, not the low value of the signal. So output of envelope detector ED will be this. So you will get something like this. Guys, is this empty or empty? Come on, tell me. Although in our case we didn't take empty, but we took empty plus 3. So it is empty plus 3 or empty plus 3? Come on, you tell me. Now let's check what is mu there. What is mu? Mu is 8 minus of minus 2, 8 plus of minus 2. It is 10 by 6, 5 by 3. So mu is 1.2, so it is 1.1 approximately. Is it greater than 1? Yes. So it is a case of what? Overmodulation. Now that is the only problem with envelope detector as well as square law demodulator, that we can only use these two techniques when mu is less than 1. So write somewhere note. Write the note guys. We add a DC term to empty before multiplying with carrier, but ensure that empty plus DC term should be positive. Empty plus DC term should be positive. And if it is positive, then we are good. What is the wrong thing happened here? What's the wrong? That it went into negative. And I also told you that I will discuss why do we need K. Right? Why do we need K? I told you that I will discuss this in envelope detector. What is the importance of K? Now guys, if you recall, in the equation of this AC1 plus KMT cos 2 pi FCT. Right? Now, suppose, see, the whole idea of this term should be positive. If it is not positive, then it's a problem. So if you look at this term only, 1 plus K or MT can go to positive as well as negative. So K what K does, suppose MT is 10 cos 2 pi FMT. So what is M of T max? M of T max is 10, M of T min is minus 10, right? So max is anyway fine, min will be 1 minus 10 if we say k equal to 1. So we're going to negative. So k, what it does, k normalize this overall so that this is k empty, right? Mod is always less than 1. Or I can also say that indirectly. 1 plus k empty mod is always greater than k. So that if it is overall positive, this term is positive, then there is not a problem. Right? That we can say. So what is the importance of k? K normalize. Because k will select some value. Suppose if this is 10, k will say, okay, I will be 1 by 20, so no problem. 10 by 20 is half. 1 plus half is 3 by 2. 1 minus half is half. So it is not going negative. It is not going below the x-axis, and that's the beauty of k, and that's why we need it. So write, note, k is used to normalize. K is used to normalize the peak amplitude of the masses signal. The peak amplitude of the masses signal so that modulation index is less than or equal to 1. So that modulation index is less than or equal to 1. So practically if you want to set k in lab exercise, so we have a component and there we can tune the value of k depending that what is the amplitude of the masses signal. So that is not a big thing. Vmax, Vmin are the highest and the lowest peaks of the masses signal after adding DC component. Yes, you are right. This Vmax and Vmin is from the transmitted part, right? From the AM signal, not only from the masses signal. And how do we generate AM? We take a masses signal, we definitely add some DC value, then we multiply with carrier signal, we get AM signal. If we don't add any DC term, it will become DSP signal. Okay, which when we'll discuss, we'll get to know. Okay. Envelope started at 5, and what is that? Is it AC or anything? It's AC signal only, but it's not only AC, it is a multiplication of one AC which is low frequency masses signal and another AC signal which is high frequency carrier signal. So it started at 5 because when we took empty, it was started from 0. Then we added, I guess, 5 volt or plus 3 something, plus 5 volt. So that 0 became 5 and the minus 5 became minus 2. So it is AC only, embedded with carrier signal. What you can do, guys, you can check some MATLAB codes for AM signal, and when you check MATLAB codes for AM signal, you will be seeing at this kind of it's very, I don't know how many of you know how to code in MATLAB, but if you see, it's very easy to code in MATLAB. And even in your college, you can go and again try and see that how the AM signal comes on the CRO. The only problem with CRO is that it takes a lot of time to do that exercise. In MATLAB, you can get it done within 5 minutes. So please try it out. If somebody needs help on that, please write a mail to the team asking about MATLAB codes and everything. I will provide, no problem. But you should know a little bit of MATLAB. Then you can get it.